Hello, everyone. Welcome to our MCAT lecture series 15-week program, week 4. I will be talking about equilibrium, solutions, and acids and bases today. And just as a reminder to everyone, if anyone wants to be added to our GroupMe, you can email me. I will link my email at the end of this lecture. This is also the link here. I have added our Instagram handle, and this is our YouTube link to our Socratic Med page. This video, as well as all of our other MCAT review videos, are on this channel. This is the link here. And just to remind everyone, we'll have 2 lectures every week, Sunday and Monday, recorded releases at 8:30 p.m. Eastern Standard Time. All right, so I have 9 questions to talk about and go over today. We will go over the questions, and then each topic that each question has, we will go over them in more detail. So question 1 here. I will let everyone read the question to themselves. So pause the video and we will then go over the question together. All right, so the question states, if the above reaction was put under stress and its equilibrium was disturbed, which situation would cause the reaction to shift toward its products to re-establish the equilibrium? So when we're looking here at this first question, so this first question and looking at this equation, we have N2 plus 3H2, and that reacts to form 2NH3, and we are given our delta H value here. So we know that it is exothermic because it is a negative delta H value. So now I will go ahead and talk through A, B, C, and D here. So for an exothermic reaction, if I increase the temperature as it says in A, then I am treating temperature as a product. So I'm trying to think of this equation in terms of adding a product. So if I add a product to this equation, and this disturbs my equilibrium, my reaction will shift to the left, so towards the reactants. And I know that A is therefore wrong. When looking at B, if I had helium gas, notice how helium is not involved in this reaction to this reaction vessel, and I do not change the pressure, then nothing will happen. Therefore, this will not shift the reaction towards the products. Now looking at C and D, I'm just changing concentrations here of 2 substances that are in this reaction. If I add N2 to the reaction vessel, then I will shift the reaction towards the products because I'm adding a reactant. If I add NH3, then I will shift the reaction to the left. And that is because I'm adding a product and it will go the other way. So therefore my answer here is C. So now I will talk about equilibrium and LeChatelier's principle. So what this problem went over that we just did was essentially LeChatelier's principle. What LeChatelier's principle says is that when a system is in equilibrium and it is stressed, the reaction will shift towards the reactants or towards the products in order to return to equilibrium. There are different situations that we can discuss here and think of. One of them is changing the concentration. Therefore, looking at this equation right here would be changing the concentrations of N2, H2, or NH3. As you see here, I will move that out of the way slightly. We also can think about changes in pressure or our change in volume. If the pressure of the system increases, the reaction will shift to the side of the equation with less moles. And we can think about that the other way. If the pressure of a system decreases, the reaction will shift to the side of the equation with more moles. Changing temperature, we can treat temperature, as we talked about, as a product. So we can, for an exothermic reaction and for an endothermic reaction, we think about it as a reactant. And then something that is not mentioned here, but we did mention in that question, was having an inert gas. So a gas that is added to this reaction that is not involved in the initial equation. If no pressure or no volume is changed in the reaction, then there will be no effect on the direction change in equilibrium. So now talking about reactions in equilibrium and maybe not in equilibrium, we have our equilibrium constant expression here. So that is our KEQ. When we see the we see KEQ here, the equation for it, which is our concentration of our products over the concentration of our reactants. We know our equation is in our reaction, is in equilibrium when our rate of formation of products equals the rate of formation of reactants. So just the rate of the forward reaction equals the rate of the reverse reaction. And then what K says is that it describes our equilibrium in terms of our concentration here, but we can also think about it in terms of pressure. And now it's just a bit of more of a deep dive into what K means for us and just specific components of it. KEQ is temperature dependent. We only take aqueous or gases as part of the reaction into this equation. So if there is a solid or if there is a liquid, we do not put that in the equation. So if one of our reactants or products was water in its liquid form, then we would not involve that into the expression. And then as you can see here, if we have a larger K value, our products are favored, meaning our reaction has shifted more towards products at equilibrium. So larger K, we favor products. And then when we think of K in the reverse reaction, as equilibrium reactions go both ways, the reverse reaction is 1 over KEQ as its equilibrium expression. Now our Q is our reaction quotient, and this is telling us the concentration of products and reactants at a given moment in time. So not when it's at equilibrium, but maybe after the equilibrium has been disturbed. So if our KEQ is greater than our Q, a reaction will proceed towards products. If our KEQ is equal to Q, our reaction is in equilibrium. If our KEQ is less than our Q, then our reaction proceeds towards reactants. And this makes sense. For example, I will explain KEQ being greater than Q. So our reaction will proceed towards products because at this given time, we have less products than we would have at equilibrium. And therefore, our reaction is going to shift to products in order to reestablish that. All right, so solutions. So this is our second question. We'll be dealing with solutions here. Again, I will let everyone read this to themselves, pause the video, and then we will discuss in a second. All right, so I will read over the question and then we will go over. So the question states, which phases of solvent and solute can form a solution? 1, gaseous solute or gaseous solvent. 2, solid solvent or gaseous solute. 3, liquid solvent or gaseous solute. So because this is a Roman numeral question, I will want to look at whichever Roman numeral appears exactly 2 times in my answer choices. Therefore, I see that Roman numeral 3 has appeared both 2 times in C and D. So I will first go over that one. So I'm looking at 3. We have a liquid solvent and a gaseous solute. I know that this can exist as this is like soda, carbon dioxide dissolved in a liquid. So I know 3 is right. I'll cross off A and B. And then I know 2 must be right as it is also in C and D. So I will evaluate 1. We have a gaseous solvent here and a gaseous solute. We also know that this can occur. Therefore, I know that my answer here is D. And this is important because all phases can be combined to form a homogeneous mixture. And that is essentially the definition of a solution. So the important point about this is that all phases can exist and form a solution. So talking specifically about what solutions, solubility, important definitions that we need to know to understand solubility is 1, solutions, what they are. As I said, they're formed when a solute and a solvent are mixed together. They form a homogeneous mixture, meaning that they're forming without anything in the way. So the definition of a solvent is the portion of a solution that remains in the same phase. It is the largest part of the solution. This is like water, for example, when we have a crystal of sodium chloride dissolved in it. So, for example, here, what happens when I have a solvent, and then what a solute would be in this case would be the sodium chloride. So if I dissolve my solute, sodium chloride, into my solvent, which is water, I will form these electrostatic interactions here, which is solvation or dissolution. And that is how I form my solution. I get the positive H pluses here interacting with negatively charged Cl minus ions. And these electrostatic interactions is what allows sodium and chloride to dissolve in water. So now what solubility is the maximum amount of substance that can be dissolved in a solvent at a given temperature. And this is all temperature dependent. And saturation is when a solution, when the dissolved solute and the undissolved solute are in equilibrium. So we have, and we know this occurs when some precipitate, which is solid at the bottom of a solution, begins to form when we have a solid solute and a liquid solvent. And solubility rules are also important on the MCAT. These rules are important to know, but is also important to understand that these are not 100% true, but these should be memorized as a rule of thumb. Sometimes solubility rules are daunting, so as there are a lot of different rules, but these rules in general work most of the time. The 3 rules to know for phases is that the solubility of solids in liquids increase with increasing temperature. The solubility of gases in liquid decrease with increasing temperature. The solubility of gases in liquids increase with increasing pressure. And then now for salts, just like sodium chloride, as we had been talking about, all group 1 metals and ammonium ion salts are soluble in water. All nitrate, perchlorate, acetate salts are soluble in water, and all silver, lead, and mercury salts are insoluble, except if they're mixed with those anions that we had just discussed previously. All right, question 3 here. We will talk about concentration. All right, again, I will let everyone read the question to themselves, and we will discuss. So pause the video, do the problem, and we will discuss shortly. All right, so this problem states a student dilutes 50 milliliters of a 2 molar solution of H3PO4 with water to end up with 250 milliliters. What is the concentration of the new solution here? So first we have to think of what the equation is that relates our molarity and our volume. So we have the equation here as M1V1 equals M2V2. And this is the work that I showed for this. We have, besides the equation, I made sure I wrote down my value for M1, V1, M2, and V2. And I basically just plugged into these values into the equation, rearranged the equation to solve for M2, and then found out my answer was 0.4. It is important to make sure that you are keeping your decimal places in place. This could potentially get you mixed up and think it is 4 molar. But this equation is important, as you'll find this not only just to find dilution, but you may also use this during titrations and other acid-base calculations. So besides the dilution equation that we had just used, other important equations and concepts to know here are percent composition by mass. So it'd be the mass of our solute, mass of solution times 100. And this is a percentage, so that is why we're multiplying it by 100%. Our mole fraction, which would be moles of our solute over the total moles of the entire solution. And this is just telling us how much of one solute we have in solution. Our molarity, again, as what we discussed, is our moles over liters. So moles of a solute over the liters of our entire solution. Now, molality, on the other hand, is our moles of solute over our kilograms of solvent. So not the kilograms of solution, but the kilograms of solvent. Another thing that you might see in textbooks or something would be our normality, which is denoted with an N. This shows up very rarely on the MCAT, so I did not think it was a high yield topic we did need to discuss. All right, now question number 4 is solubility. I will let everyone read this question to themselves and pause the video, and we will discuss. All right, so the question states the KSP of CaF2 is 3.9 times 10 to the 11th, and the KSP of PbF2 is 4.0 times 10 to the negative 8th. Now, which of the following is true? So it is important here to think about first what KSP is telling us. KSP is telling us the solubility of substances in solution here. So in this case, the solubility of CaF2 and the solubility of PbF2. When we look at A and B, this is asking us the rate of the reaction and the energy involved in the reaction. Our KSP doesn't tell us anything about these values, so therefore we would A and B cannot be right, and we would have to cross those off. Now, evaluating C and D, we do know we can use KSP to figure out which one is more soluble. So looking at both of our KSP values here, we know that PbF2 is more soluble because it is a larger number. This means that the reaction is tending towards products, and that means that in its ion form. So therefore, the answer here is D. So now I would talk about KSP as well as IP, which is the ion product. So what the KSP here is the equilibrium constant for the solubility of a saturated ionic compound. as we talked about K in general, K is also temperature dependent. And then what IP here is, it's essentially K. So it's the same equation as K, but it's our value at a given point in time and not at equilibrium. And then also for an unsaturated and supersaturated solutions, our IP value is going to be, for unsaturated, our IP value is going to be less than our KSP. And what unsaturated means is that it's a solution that is not yet at equilibrium, meaning that more reactants can be added without forming a precipitate. And supersaturated is when we've already formed precipitate and nothing more can dissolve. So even more precipitate will be added if more particles are added. Now, the common ion effect. So this is an interesting thing that can happen when we add an ion common to two solutes to a solution. So when I look at this picture here, I see I'm adding AgCl into a beaker of water. I will get, its normal KSP value by doing this. But now in this case, if I already have NaCl in this solution with water, and then I add AgCl, my solubility will decrease. And if I am looking at this equation over here, the reason for this is that I have chloride ions already in solution. So when I add my AgCl, my reaction isn't going to proceed forward as much. It is going to stay more in its solid form. Therefore, my KSP value will not be as much as it would if there was no ions already in solution. And what this is just essentially LeChatelier's principle. All right. So next we have complex ion formation and relating that to solubility. So what a complex ion is, we have a cation that's surrounded by ligands. In this case, the ligand would be a Lewis base. So if I look at Ag forming with NH3, forming a bond with NH3 in solution. So this would occur if I throw AgCl into, or I throw NH3 into an AgCl solution. So why this is important is because this can increase the solubility of Ag plus. Ag will form a coordinate covalent bond with two molecules of NH3 as seen in this picture. And these are called coordinate covalent bonds. So my NH3 will donate an electron to Ag, and another one will also donate its electrons, therefore a Lewis base. And this overall will have this molecule as a positive charge, and it will be able to form bonds more readily with water in solution. All right, so question 5. So now we're going to switch gears slightly and talk about acids and bases. So the first question here, which of the following is not a Bronsted-Lowry acid? I will give everyone a little bit and pause the video so you can solve this problem. All right. So when approaching this problem, I have to know what a Bronsted-Lowry acid is. These are proton donors, and we have to evaluate their structures to see which one will donate a proton. So here I drew out A. I have my hydrogen bonded to my chloride. I have nitrogen bound to 3 hydrogens. And I have here my acetic acid, and I have sulfuric acid. So in this case, I know A is an acid, as Cl minus can exist stably, as if I do lose this hydrogen. When I look at C, I also know I have this OH group, which is also acidic. And if I have these two negative if I have this negative charge here, this can be resonance stabilized, so I know it would be stable if the hydrogen left. And same thing goes for sulfuric acid here. However, when I look at my NH3, this will actually want to gain a hydrogen and not lose a hydrogen. The N would attack another substance with a hydrogen. The lone pair of electrons on nitrogen would attack another substance with hydrogen and would therefore be a Bronsted-Lowry acid by gaining another hydrogen. So just to go over the definitions of acids and bases, we just talked about Bronsted-Lowry acids, which are proton donors. Bronsted-Lowry bases are proton acceptors. Another definition is Lewis acids, which are electron acceptors, and Lewis bases are electron donors. We also have the definitions here of Arrhenius acids and Arrhenius bases. These also aren't super important for the MCAT, but it is important just to be aware of the definition of them. So Arrhenius acids increase hydronium ions in water when dissolved, and Arrhenius bases dissociate into hydroxide ions when in water. All right, question 6 here. So this is the question now about the strengths of acids and bases. All right, so here's the first question. Pause the video, read it to yourself, and we will go over it. All right, so I will read the question out loud, and then we will discuss. So the question states, what is the concentration of a 1 molar solution of HF? And I am provided with the Ka value here. So what I would have to do would be set up an ice table. So I would have to draw out the reaction first of HF dissolving in water. And so I have done that right here. So I have my hydrofluoric acid and water, and then I have my hydronium ion and fluoride ion. And this is what happens when I dissolve HF in water. So my ice table here is I am showing my initial values of molarity. My C is my change, and then my E is the value at equilibrium. So I have my Ka equation here, which is important because I know my Ka value. So I can define, so I can use and find the values that I do not have. So from my ice table, I can plug in these values. I can plug in my Ka value. I know for my fluoride ion, H3O plus is X. And then for HF, it's 1 minus X. However, X is going to be small compared to my other values in this. So therefore, I can just say that I can think of it as negligible and just say 1. So then I just use 1 and I don't worry about this minus X here. And then I take the square root of my Ka value and I find the concentration for the hydronium ion and the fluoride ion. All right, so the dissociation constants specifically, we have Ka, Kb, and we also have Kw, which is the equilibrium constant for the autoionization of water. So now looking at Ka specifically, so K tells us in terms of K or Kb, K is telling us how much an acid or base dissociate or ionizes in water. The larger the Ka value is going to mean a stronger acid. And then when we think of this in terms of pKa and pKb, the smaller the pKa or pKb value, the weaker the stronger the acid or base. So if I have a low pKa value, I am going to have a strong acid. For base here, Kb is the equilibrium constant for the dissociation of a base. And our pKa, or our pKb, sorry, is a negative log of Kb. And essentially what P means, this is just, P is just a negative log. The reason that we use this is because it makes the values more tangible. They make them cleaner, easier to deal with. When we look here at our pKa, we have pKa and pKb is equal to 14. These are 14 is an easy number to work with. When we were just using our concentration here for H3O plus and H minus or OH minus, 1 times 10 to the negative 14 is a little bit of a harder value to work with. And then also when we are relating our Ka and Kb together, we see that Kw is equal to Ka times Kb. All right, so now talking about acids specifically, a strong acid will completely ionize, completely dissociate when dissolved in water. Our Ka value for strong acids will be greater than 1. And as we discussed, the larger the Ka value, the stronger the acid. And then weak acids, on the other hand, do not completely dissociate in water. So when we look at this equation up here, we have Ha plus H2O is in equilibrium with H3O plus and A minus. So we have our Ka value here. And when we look at this graph, we see it's dissolved in solution. We know this is a weak acid because we still have, after dissociation, we still have some Ha in solution, where if this was a strong acid, we would no longer have any Ha and it would all be H3O plus and A minus, as this reaction would completely ionize and be complete. Going back to strong acids, it is important to know the 6 strong acids that you see here. So I would recommend to go back to this chart and to make sure you have those memorized. So now strong and weak bases. Strong bases dissociate or ionize completely in water, while weak bases do not. The strong and weak bases, or sorry, the strong bases that are important to know are in this chart here. I would also add here sodium, lithium, and potassium oxides, and then also metal amides, so a metal with NH2. All right, so now I will talk about pH specifically, pOH, and also concentration of H plus ions and concentration of OH minus ions. All right, so here is question 7. Read it to yourself, pause the video, and we will discuss. All right. So the question states, what is the H plus concentration in a solution of HCl when the pOH is 12? So this question is testing our ability to interconvert between pOH, pH, and then concentration. So we have to know how to do this readily. We have to know that our pH plus our pOH is equal to 14. So we first figured that out. As we see here, our answer is A, but I will discuss the process that I used to get there. So I wrote down my pOH value, and I know that my pH is going to be 14 minus 12, as pH plus pOH equals 14. I find my pH is equal to 2, and then I also know that 10 to the negative pH power is equal to my hydrogen ion concentration. So therefore, I find that as my answer is A, which is 10 to the negative 2. And this is also important in order to be, it's important to be diligent about knowing where you are putting your decimal points. This is, you have 10 to the negative 2, and you know this. is one of these values and not anything else. And also knowing that these two are actually the same. All right. So now talking specifically about pH and relating that to acidity basicity, our pH and our pOH are easy ways to demonstrate H plus and OH minus concentrations. And that is the same reason that when we discussed our pK, pKb with our Ka and Kb, it's just a easier and cleaner way to look at these numbers. The relationship between pH and H plus concentration is pH is equal to the negative log of H plus. For pOH, it is pOH is equal to the negative log of OH minus. And as we discussed, the pH plus pOH equals 14. And then we know when we are looking at pH and the numbers associated with them, if the pH is greater than 7, we have a basic solution. If the pH is equal to 7, we have a neutral solution. And if the pH is less than 7, we have an acidic solution. All right, so this chart specifically, I would encourage everyone to memorize and know how to do this. It is important on the MCAT to be able to quickly like interconvert between these values. You might come across a problem that requires you to do this, possibly even as a first step of a problem. So it would be important to be able to do this quickly so you can get through the problem in ample time. And another thing I would recommend too would be to possibly draw this out from memory to make sure you do actually really know this. All right, question 8, reactions with acids and bases. Again, read this to yourself and pause the video. I will go over it in a minute. All right, so the question states, which of the following best describes the conjugate acid in the equation below? So the equation is HCl plus H2O yields H3O plus Cl minus. So first, I'm going to need to determine what the conjugate base is. For a Bronsted-Lowry acid and bases, it's the substance that is going to lose a proton. So I see here I have HCl and H2O. I see H2O becomes H3O plus, therefore it is gaining a hydrogen, while HCl actually loses a hydrogen. Therefore, I know that my conjugate base is going to be Cl minus. And therefore, the answer is C. So I know that HCl is a strong acid. When I dissolve this in solution, it's going to react completely. Therefore, Cl minus will not have any tendency to gain hydrogen ions anymore. And then there's a different situations in terms of using a strong acid, a weak acid, weak base, and strong base, and what our conjugate base will act as, or our conjugate acid will act as, and we will discuss that in the slides further. All right, so looking at here, we have HF plus H2O. So we have HF in our solution with water. And so we're going to see the strength of the acid-base pair here. So our acid is HF, and our conjugate base is F minus. So HF, which is a weak acid, what will what will the fluoride ion be? And that will be also a weak base. So if we have a weak acid or a weak base, the conjugate will also be weak. For NH3, this is a weak base. So our conjugate acid, which is NH4 plus, the ammonium ion will also be weak. And then just to sum that all together, our conjugate base of a strong acid will have no basic properties in water. So therefore, our conjugate acid of a strong base will have no acidic properties in water. And then our conjugate base of a weak acid is a weak base, and vice versa. So neutralization reactions, this is when we combine an acid and a base and we form water and salt. It is important to know that if we mix equimolar amounts, so if they have the same molarity, an acid and a base together, it will go to completion and completely neutralize no matter the strength of the acid or base. This will happen all the way to completion. Next is hydrolysis of salts. So this is when we have a salt and we put it in water. So in this case of this equation here, we have NaF, which is our salt, and we dissolve it in water. And what we want to think of for the hydrolysis of salts is what our solution will be. Will it end up being neutral? Will it end up being acidic? Or end up being basic? So we will know that if we have a strong acid and a strong base, we will form a neutral solution. If we have a strong acid and a weak base, it will form an acidic solution. But with a weak acid and a strong base, that'll form a basic solution. So when looking at this equation here, we have NaF, and that splits off into HF and NaOH. Here, NaOH is strong, so it's going to completely dissociate and not exist in this form at all. It will exist in its ionic form. HF, on the other hand, is weak, so it'll exist in this as this expression right here. So we won't have that much HF existing in solution. We will have a lot of the hydroxide ion in solution. Therefore, that's how we know that when we have a weak acid and a strong base, we will get a basic solution. All right, our last question here is question number 9. Talk about buffer solutions, indicators, and titrations. All right, so here's our last question. Pause the video and we will discuss when you are done. All right, so the question states, what is the pH of a solution with an ammonium ion concentration of 60 millimolar solution and an ammonia concentration of 600 millimolar concentration? And it also is telling us that our pKa is 10.55. So this is something where we need to know the equation that relates our pH and our pKa values. So I will show the work that I did to get this answer. So this equation here is the Henderson-Hasselbalch equation, and this is what relates these two equations in a buffer solution. So as you can see here, I have pH equals pKa plus the log of my conjugate base and the weak acid concentration here. All right. And then I wrote down the concentrations that I do have. I have 600 times 10 to the negative third molar, 60 times 10 to the negative third molar. And then in order just to make these calculations easier, I made these two the same, so I could cross this out in this part of the equation once I plug it in, and then I get log of 10 to the 1. And I know log of 10 to the 1 is just 1, so I add that together and I get that my pH was 11.55. All right. So titrations. So I'll talk specifically about the titrating a strong acid and a strong base, and then vice versa. So the different parts of a titration curve are important. and what titration is specifically. We use titrations to determine the identity of a weak acid or a weak base. And the one that we don't know is our analyte. And then the one that we do know is our titrant. So when looking at this one here, for example, we start off with a strong acid, and we don't know the concentration of our strong acid here, but we are adding a known concentration of the strong base that we're adding. This region right here is called the buffering zone. So this is where we resist a change in pH. This will happen for a while, and then all of a sudden, the solution will no longer be able to resist a change in pH, and this will spike exponentially. And then there are, besides the buffering zone here, there are two other values that are important to know. Right here, where this big spike occurs, we have our equivalence point. This is exactly the same. We know that exactly the same amount has been added in order to neutralize that reaction. So we have exactly the same amount of strong acid, and we actually have the same amount of strong base as well. Additionally, the midpoint or the half equivalence point, which would be the point midway between the equivalence point and when we just began here. And that is when the concentrations of the conjugates are equal. So not what is being added, but the conjugates of what is actually in this reaction. So let's say the strong acid in this reaction was HCl. It would be HCl and its conjugate base Cl minus would be equal. And we know that we will get that our equivalence point right here will be for strong acid and strong base will be at 7. If we have a strong acid and a weak base, that'll be a little bit different. We see that it occurs. Oh, sorry. So we have a so here we have a weak acid and a weak base. This actually should say strong acid here. Strong acid and weak base. We know this will be, because it's a strong acid, it will be acidic. Here, this is a weak acid and weak base also actually occurs at the pH here will be 7. And then here, when we have a weak acid and strong base, the equivalence point will occur at being basic. Here we have our Henderson-Hasselbalch equation, which we talked about. This is an important equation to make sure you have memorized. All right, now, lastly, we will talk about buffers and indicators. What buffer solutions are specifically are a mixture of a weak acid and its salt. So a mixture of a weak acid and its salt is like what you see in the bicarbonate buffer system. This is really important for the MCAT, mostly seen in the biochem section, but this is a buffer that is really important to know. Now, what indicators are, these are weak acids or weak bases that change color at the endpoint of a titration. So the endpoint of a titration is pretty close to what the equivalence point is, so it actually can estimate it pretty well. These questions could be asked in terms of which it'll give you maybe a few of these options and say like which one it will work best in this solution. And you will want to pick one that has the pH color change close to the pKa of the solution that you are referring to. All right, and that is it for the lecture for today. If you have any questions about this or any other topics, feel free to reach out. This is my email. And if you also want to get into the GroupMe, you can send me an email or look earlier in the slides to get that link. I will be posting these slides in our GroupMe. So if anyone wants to see them specifically, they will be able to do just that through the GroupMe. All right. Good luck studying, everyone.